Let's explore binary search trees, often abbreviated as BSTs. We'll cover their fundamental properties, common operations, and how they're implemented. Let's explore the fundamental properties that define a binary search tree. First, for any node in the tree, all elements within its left subtree are less than the value of that node. Secondly, for any node, all elements in its right subtree are greater than the node's value. Thirdly, both the left and right subtrees must also be binary search trees themselves, adhering to the same properties. Next, an Inorder traversal of a binary search tree will produce a sorted sequence of the elements. Finally, binary search trees enable efficient searching, insertion and deletion operations. The average time complexity for search, insert and delete operations is big O of log n, making them quite efficient. However, in the worst case, such as with skewed trees, the time complexity can degrade to big O of n. The space complexity, that is the space required to store a binary search tree with n nodes, is big O of n. Recursive operations within the tree utilize big O of h stack space, where h represents the height of the tree. Let's examine the structure of a node in a binary search tree. A typical node, which we'll call a tree node, consists of three key components: a value which holds the data stored in the node, a left pointer which points to the left child node, and a right pointer which points to the right child node. Here's an example of how you might implement a tree node in Python. We define a class called treeNode. The init method initializes a new node with a value, a left child and a right child. We can create a simple binary search tree by first creating the root node with a value of 50. Then we assign a left child with a value of 30, and a right child with a value of 70. Now let's delve into the search operation within a binary search tree. Here's how you can implement a search function in Python. First, we define the search function, which takes the root of the tree and the key value to search for as input. The base case checks if the root is none, meaning the tree is empty, or if the root's value matches the key. In either case, the root is returned. If the key is greater than the root's value, we recursively call the search function on the right subtree. Otherwise, if the key is smaller than the root's value, we recursively call the search function on the left subtree. For example, if you are searching for the value 60, the search path is highlighted on the visualization. The value is found at the highlighted node. Now let's take a look at the insertion operation in a binary search tree. To insert a new node into a binary search tree, we can use the following Python implementation. First, we define the insert function, which takes the root of the tree and the key value to insert as input. If the tree is empty, meaning the root is none, we create a new tree node with the given key and return it. Otherwise, we recursively traverse the tree to find the appropriate position to insert the new node. If the key is less than the root's value, we recursively call the insert function on the left subtree. If the key is greater than the root's value, we recursively call the insert function on the right subtree. Finally, we return the unchanged node pointer. For example, the path is highlighted on the visualization to insert the value 55. The new node with the value 55 is inserted as the left child of 60. Now let's explore the deletion operation in a binary search tree. There are three primary cases to consider when deleting a node from a binary search tree. Case 1, if the node to be deleted has no children, meaning it is a leaf node, simply remove the node from the tree. Case 2, if the node to be deleted has only one child, replace the node with its child. Case 3, if the node to be deleted has two children, replace the node with either its Inorder successor, which is the smallest value in the right subtree, or its predecessor, which is the largest value in the left subtree. Consider the following deletion examples. Case 1, to delete the leaf node 20, simply remove it from the tree. Case 2, to delete the node 30, which has one child, replace it with its child 40. Case 3, to delete the node 50, which has two children, replace it with its Inorder successor 60. The result after the deletion is illustrated. Now let's discuss tree traversal methods for binary search trees. There are three common types of traversals. First, Inorder traversal, which visits the left subtree first, then the current node and then the right subtree. This results in a sorted order of the nodes. Secondly, Preorder traversal, which visits the current node first, then the left subtree and then the right subtree. Thirdly, Postorder traversal, which visits the left subtree first, then the right subtree and then the current node. As illustrated on the visualization, the visit order for each traversal method is highlighted on each node. The order of execution for Preorder is 1, 2, 3, 4, 5, 6, 7. The order of execution for Inorder is 1, 2, 3, 4, 5, 6, 7. The order of execution for Postorder is 1, 2, 3, 4, 5, 6, 7. Now let's explore some of the key applications of binary search trees. First, searching and sorting. Binary search trees provide efficient searching and maintain sorted order, making them ideal for database indexing, symbol tables and compilers, and efficient implementation of sets and maps. Secondly, priority queues. Binary search tree variants like heaps can implement priority queues, useful for task scheduling and operating systems, event-driven simulations, and process management. Thirdly, hierarchical data. Binary search trees are perfect for representing hierarchical relationships such as file systems, organization charts, and XML or HTML document object models. Finally, computer graphics. Binary search tree variations optimize spatial data for rendering, collision detection using binary space partitioning trees, 3D scene rendering, and range searching in game environments. Let's compare standard binary search trees with balanced binary search trees. Standard binary search trees can degenerate into a linked list, resulting in big O of n operations. This leads to a worst-case time complexity of big O of n for search, insert, and delete operations. However, they offer a simpler implementation. Balanced binary search trees, on the other hand, guarantee big O of log n performance, ensuring consistent performance for all operations. However, they require a more complex implementation due to the need for rotations to maintain balance. As illustrated in the visualization, a skew tree can result from a standard binary search tree, whereas self-balancing trees are represented by balanced binary search trees such as AVL and red-black trees. Let's summarize the key takeaways about binary search trees. Firstly, binary search trees combine the navigational efficiency of binary trees with the rapid lookup capability of ordered arrays. Secondly, core operations such as search, insert, and delete have an average time complexity of big O of log n, but can degrade to big O of n in the worst case. Thirdly, traversal methods, including Inorder, Preorder, and Postorder, facilitate different processing orders and applications. Fourthly, balanced variants such as AVL and red-black trees optimize performance by maintaining tree balance through rotations. Finally, binary search trees are fundamental to many applications, including database indexing, priority queues, memory management, and spatial data organization. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.